Hello, friends. Welcome back to another journey through the quiet corners of the cosmos. Tonight, I want to ask you something that might sound strange at first. When you look up at the night sky, what do you see? Stars, certainly. Maybe the moon, perhaps a planet or two if you're lucky. But here's what most of us miss, what we don't see: the spaces between. The vast, silent stretches where nothing seems to exist at all. What if I told you that these empty places, these cosmic voids, aren't just gaps in the universe? What if they're actually the largest structures that exist? What if the nothingness is what shapes everything? If you're enjoying these quiet explorations of space and science, I'd be grateful if you'd like this video and subscribe to the channel. It helps these stories reach others who, like you, find peace in the mysteries of the universe. Now let's drift deeper into the darkness together. Imagine standing in your backyard on a clear night. You count the stars, you can see maybe a few thousand if you're far from city lights. Now imagine having a telescope powerful enough to count galaxies instead of stars. You'd see millions of them scattered across the sky like luminous seeds. But here's what would truly astound you: between all those galaxies, between all those clusters and clouds of cosmic matter, there are regions so empty, so devoid of anything, that they make the space between stars look crowded by comparison. These are the cosmic voids, and they're incomprehensibly large. In 1978, two astronomers named Stephen Gregory and Laird Thompson were doing something rather routine, mapping the positions of galaxies in a particular region of space called Boötes, named after the constellation. They expected to find galaxies scattered somewhat evenly, perhaps clustered here and there, but generally distributed the way we'd come to expect. What they found instead stopped them cold. There was nothing there, not just a small gap, not just a region with fewer galaxies. An enormous spherical volume of space, roughly 330 million light-years across, containing almost no galaxies at all. In a region where they should have found thousands of galaxies, they found approximately 60 galaxies in a space that could contain tens of thousands. They discovered what would come to be called the Boötes void. Some called it the Great Nothing. Others, more dramatically, called it the super void. Think about that scale for a moment. 330 million light-years. If you could travel at the speed of light, the fastest speed possible in our universe, it would take you 330 million years just to cross from one side to the other. The entire history of complex life on Earth, from the first simple organisms to this moment, spans only about 600 million years. You could live that entire evolutionary journey twice and still not have crossed the Boötes void. And here's what makes this discovery even more remarkable. The Boötes void isn't unique. It's not some strange anomaly, some cosmic accident. It's normal. Voids like this are everywhere. Scientists estimate that cosmic voids make up approximately 80% of the observable universe by volume. 80%. Let that settle in your mind. Everything we think of as the universe, all the stars, all the galaxies, all the planets, and black holes, and nebulae, all of it exists in just 20% of the available space. The rest is void. We live in a universe that is mostly nothing. But here's where our understanding begins to shift, where the story becomes more interesting. These voids aren't actually empty in the absolute sense. they do contain some matter, some stray hydrogen atoms, some faint galaxies, some dark matter. The density is simply extremely low compared to the regions we call walls and filaments, where galaxies cluster together. If you were somehow floating in the center of a cosmic void, looking out in all directions, you would see darkness. Not the darkness of night here on Earth where you can still see stars. True darkness. The nearest galaxy might be 50 million light years away, so distant that even if it were as bright as the full moon, you wouldn't see it with the naked eye. You would be alone in a way that's almost impossible for us to comprehend. The discovery of the Buddha's void changed cosmology forever. Before 1978, astronomers generally believed that galaxies were distributed more or less uniformly throughout space, perhaps, with some clumping due to gravity, but nothing too dramatic. The voids revealed that this was wrong. The universe has a structure, a vast, intricate architecture. And here's something that still puzzles scientists today. We don't entirely understand why voids are so empty. Oh, we have theories, and we'll explore them in the chapters ahead. But the precise mechanisms that create and maintain these enormous empty regions are still being debated. Some voids seem to be expanding, pushing galaxies away from their centers. Others appear more stable. Some contain surprising amounts of hot gas that we can only detect with X-ray telescopes. Each void is in its own way unique. Think of it this way. If the universe were a city, galaxies wouldn't be scattered evenly throughout like houses on a suburban grid. Instead, they'd be clustered along certain streets and avenues, the filaments with buildings packed together at major intersections, the clusters. And between these cosmic boulevards, vast empty lots, abandoned zones, the voids. But unlike an abandoned lot in a city, which is simply space that hasn't been developed yet, cosmic voids seem to resist being filled. As the universe expands, the voids expand with it, often faster than the expansion rate of the universe as a whole. It's as if the emptiness itself has a kind of momentum, a preference for remaining empty. This brings us to a profound realization. In the universe, absence is not passive. Emptiness is not merely the lack of something. The voids actively shape the cosmic web. They push matter away. They influence how galaxies form and evolve. They may even hold clues to the nature of dark energy, that mysterious force causing the universe's expansion to accelerate. There's a parallel here that I find deeply moving. In music, silence isn't just the absence of sound, it's what gives structure to melody. The rests between notes create rhythm, meaning beauty. Without silence, music would be noise. In the same way, the cosmic voids aren't just empty space, they're what gives shape to the universe. They're the silence between the notes of creation. When Gregory and Thomson first published their findings about the Buddha's void, many scientists were skeptical. Surely, they thought, if you looked deeper with better telescopes, you'd find more galaxies filling in the gap. But as technology improved, as surveys became more sensitive, the void remained. In fact, astronomers found it was even emptier than initially thought. And then they started finding more voids. Lots of them. There's the local void, which remarkably we ourselves are perched on the edge of. There's the giant void in Canes Venatici, about 1.5 billion light-years across. There's the Eridanus supervoid, which might be responsible for one of the strangest mysteries in cosmology, a cold spot in the cosmic microwave background that shouldn't exist according to our current understanding of physics. Each discovery raised new questions. How did these voids form? Why are they roughly spherical? What's inside them really? Are they truly expanding? And if so, what's pushing them apart? The more we learned, the more we realized how little we understood about the structure of the universe. We had spent centuries studying matter stars, galaxies, planets, only to discover that we'd been studying the exception, not the rule. We'd been focused on the notes and ignored the silence. Here's a misconception I want to address before we go further. When people hear about cosmic voids, they sometimes imagine them as holes in space itself, as if the fabric of the universe has been torn away. This isn't correct. Space exists in the voids, just as it does everywhere else. It's simply that the matter that fills most of space, the gas, the dust, the dark matter, is distributed very unevenly. The voids have it. The filaments have much more of it. Think of it like air in a room. The air molecules aren't distributed perfectly evenly. There are slight variations in density. But you wouldn't say there are holes in the air where no molecules exist. The voids are similar, just on a vastly larger scale and with much more extreme differences in density. Another common question, are the voids completely devoid of galaxies? No, not quite. Even in the Bode's void, there are about 60 known galaxies. But these void galaxies are strange. They tend to be smaller, bluer, and more actively forming stars than their counterparts in the denser regions of the universe. They're like isolated villages in a vast desert, developing in their own unique ways, largely undisturbed by neighbors. Scientists study these void galaxies carefully because they offer a glimpse of how galaxies evolve in isolation without the constant gravitational interactions and mergers that characterize life in the crowded cosmic neighborhoods. It's galactic evolution on easy mode. In a sense, slower, gentler, less dramatic. As I share these facts with you, I wonder, have you ever experienced a moment of true emptiness? Not loneliness, but genuine solitude, where the absence of stimulation of noise of other people allowed something else to emerge. Perhaps a clarity of thought, or a deep relaxation, or simply an awareness of your own existence that's normally drowned out by the constant presence of everything else. The cosmic voids invite us to consider the value of emptiness in our own lives. We live in a culture that fears voids, that fills every moment with sound, every space with activity, every silence with words. But the universe itself suggests a different model. Perhaps emptiness isn't something to fear or fix. Perhaps it's essential to the structure of things. Scientists sometimes describe the cosmic web, the pattern of voids, filaments, and clusters, as resembling a sponge. The solid parts of the sponge are where galaxies live. The empty chambers are the voids. But here's the beautiful part. You can't have a sponge without both elements. The holes define the structure as much as the solid parts do. Or think of it like foam on the surface of water. The bubbles of air, the voids, are held in place by thin films of liquid, the galaxy filaments and walls. The foam is mostly air, but it's the liquid that gives it shape and structure. Neither element could exist in that form without the other. The Bode's void is about 25 times the diameter of our own Milky Way galaxy. Imagine our galaxy as a grain of sand. The boat is void would be a beach ball. And remember, this is just one void among countless others threading through the universe. When you grasp the true scale of these structures, something shifts in your perspective. The concerns that loom large in our daily lives, our deadlines, our disagreements, our anxieties, they don't disappear, but they're placed in context. We are tiny creatures on a small planet, orbiting an ordinary star in one galaxy, among billions, in a universe that is mostly empty space. And yet here we are, aware, thinking, wondering about it all. The voids remind us that existence is improbable, that matter clumping together to form stars and planets, and life is the exception, not the rule. We live in the rare places where something happens. The voids are where nothing much happens at all, and there's so much more of them than there is of us. But here's what I find. Most remarkable scientists are now beginning to think that the voids aren't just passive, empty regions. They might be active participants in cosmic evolution. The expansion of voids might drive the flow of matter in the universe. The dark energy that permeates all of space might be most apparent, most measurable in these vast empty regions, where its effects aren't masked by the gravity of dense matter. In other words, to understand the universe, we need to understand its emptiness as much as its fullness. We need to study the silence as much as the sound. As we settle in tonight, as your breathing slows and your thoughts begin to drift, consider this: you are made of matter that once existed in those cosmic voids. Billions of years ago, the atoms that now form your body were floating in the emptiness between galaxies. They were gathered up by gravity, compressed into stars, forged into heavier elements, scattered by supernovae, and eventually incorporated into the dust cloud that formed our solar system. You carry the void within you, and someday, when our sun dies and the earth is no more, those atoms will return to space, perhaps to drift once again through the silent darkness of a cosmic void, waiting for the next chapter in their endless journey. The voids teach us about perspective, about scale, about the nature of existence itself. They show us that the universe is far stranger and more structured than we once imagined. They challenge our assumptions about what's important, what's normal, what's even possible. But perhaps, most importantly, they invite us to make peace with emptiness, to see it not as something frightening or wrong, but as something essential, beautiful, and full of potential. And speaking of structure and potential, we've only just begun to understand how these vast, empty regions came to be. In our next chapter, we'll travel back to the moment when astronomers first realized the universe had architecture, when the smooth, uniform cosmos of their imagination gave way to a reality far more intricate and surprising. We'll meet the scientists who mapped the cosmic web, who discovered that we live not in a random scatter of galaxies, but in a carefully structured foam of matter and void. We'll learn how a simple survey of galaxy positions revealed the largest structures in the known universe. Picture yourself as an astronomer in the 1960s. You have access to some of the best telescopes in the world. You've spent your career studying galaxies, those vast islands of stars scattered across the cosmos. And you believe, as most astronomers do, that these galaxies are distributed more or less evenly throughout space. Perhaps they cluster a bit here and there due to gravity, But overall, the universe is fairly uniform. Democratic even. Now imagine discovering that everything you thought you knew was completely wrong. That the universe isn't uniform at all. That it has a structure so vast, so intricate, that it challenges the very foundations of cosmology. This is exactly what happened. And the story of how we discovered it is one of the most fascinating detective stories in the history of science. Before we go deeper into this cosmic mystery, if you're finding these explorations meaningful, I'd love it if you'd take a moment to like this video and subscribe. It truly helps us continue sharing these quiet journeys through space and time. Thank you for being here. Let's go back to 1977. A young astronomer named Robert Kirshner was working with a team at the Smithsonian Astrophysical Observatory. They were conducting what seemed like a straightforward project, measuring the distances to galaxies in a region of the sky called Bodas. The work was tedious. They had to point their telescope at each galaxy, take a spectrum, a breakdown of the galaxy's light into its component colors, and then measure how much that light had been redshifted by the expansion of the universe. The amount of redshift tells you how far away the galaxy is. Night after night, they collected data, galaxy after galaxy. And as they plotted their results, something strange began to emerge. Or rather, something failed to emerge. In a spherical region of space, roughly 300 million light-years across, there were almost no galaxies. The telescope kept finding empty space. They checked their instruments. They recalibrated their measurements. They looked again and again. The void remained. When they published their findings in 1978, the astronomical community was stunned. Many were skeptical. Surely, they argued, this had to be a mistake. Perhaps the void wasn't really empty. Perhaps it just contained galaxies that were too faint to detect with current technology. Or perhaps the survey had simply missed them somehow. But Kirshner and his team were confident in their work. They called it a hole in space. The media, always eager for a dramatic story, dubbed it the Great Nothing. Scientists, slightly more reserved, settled on the Bodas void. What made this discovery so revolutionary wasn't just that they'd found one large empty region. It was what this implied about the structure of the universe as a whole. If one void this large existed, there might be others. Many others. The universe might not be uniform at all. It might have architecture. And that's exactly what subsequent surveys revealed. In the early 1980s, a team led by Margaret Geller and John Huchra at Harvard Smithsonian Center for Astrophysics began an ambitious project, the Center for Astrophysics Redshift Survey, or CFA survey for short. Their goal was to map the three-dimensional positions of thousands of galaxies in several slices of the sky. The work was painstaking. Remember, this was before computers became powerful and ubiquitous. Every spectrum had to be carefully analyzed. Every distance had to be calculated by hand. It took years. But in 1986, when they published their first results, the astronomical community was once again shocked. The galaxies weren't scattered randomly at all. They were arranged in sheets and filaments, great walls of galaxies surrounding enormous empty regions. Voids, plural. Not just one anomaly, but a pattern, a structure. Geller described it as looking like soap bubbles. The galaxies formed the thin films of the bubbles, while the voids were the air inside. The universe, it turned out, was foam. Think about how radical this was. For decades, the prevailing model of the universe, called the cosmological principle, held that on large enough scales, the cosmos should look the same everywhere. It should be homogeneous and isotropic, meaning uniform in density and the same in all directions. This principle wasn't just a casual assumption. It was fundamental to Einstein's equations of general relativity. It was baked into the Big Bang theory itself. And now, here was evidence that the universe had enormous structures, voids, and walls spanning hundreds of millions of light years that seemed to violate this principle. Or at least they suggested that large enough scales was much larger than anyone had imagined. The most dramatic discovery came in 1989 when Geller and Hucra identified what they called the Great Wall, a sheet of galaxies stretching more than 500 million light-years across space. It was the largest known structure in the universe at the time, and it was bordering several enormous voids. I want you to really absorb this scale. 500 million light-years. If you left Earth today, traveling at the speed of light, again, the fastest possible speed in the universe, you would arrive at the other end of the Great Wall in the year 500, 024. The entire span of recorded human history from the first written words to this moment is about 5,000 years. You would have to live that entire journey 100,000 times to cross the Great Wall. And this structure isn't unique. As surveys continued and technology improved, astronomers found more and more of these vast cosmic structures. The Sloan Great Wall, discovered in 2003, is even larger, over 1 billion light-years long. The Hercules Corona Borealis Great Wall, identified in 2013, spans 10 billion light-years, though some scientists debate whether it qualifies as a single structure. But here's what I find most intriguing. It's not the walls themselves that are the primary feature. It's the voids they surround. The walls exist because the voids pushed them there. Let me explain. In the early universe, just after the Big Bang, matter was distributed fairly evenly. Yes, there were tiny quantum fluctuations, microscopic variations in density, but nothing dramatic. As the universe expanded and cooled, gravity began to pull matter together in the slightly denser regions. Meanwhile, in the slightly less dense regions, matter was pulled away. This created a feedback loop. The dense regions got denser, eventually forming galaxies and clusters. The sparse regions got sparser, becoming voids, and this process happened on every scale, simultaneously. Small voids, medium voids, enormous supervoids, all nested and interconnected like a cosmic Russian doll. Computer simulations of this process run by teams around the world produce results that match what we observe remarkably well. The Millennium simulation, completed in 2005, tracked the gravitational interactions of over 10 billion particles from shortly after the Big Bang to the present day. When you watch an animation of this simulation, you see the cosmic foam emerge naturally from simple physics. No special mechanisms needed, just gravity, dark matter, and time. But here's a question that still puzzles scientists. Why are the voids so empty? Gravity should cause at least some galaxies to form even in underdense regions. Yet many voids contain far fewer galaxies than our models predict. Something is keeping them unusually devoid of matter. One possibility is that the voids are actively expanding. As the universe expands overall, the voids expand even faster, pushing galaxies away from their centers toward the denser walls and filaments. Studies of galaxy velocities support this idea. Galaxies near void boundaries do appear to be flowing away from void centers. Another factor might be dark energy, that mysterious force causing the universe's expansion to accelerate. In the dense regions where lots of matter clusters together, gravity can partially counteract dark energy. But in the voids where there's very little matter, dark energy dominates. The voids become zones where the accelerating expansion of the universe is most apparent. There's also the role of dark matter to consider. Dark matter makes up about 85% of all matter in the universe, but we can't see it directly. We only detect it through its gravitational effects. The cosmic web isn't really made of galaxies at all. It's made of dark matter. The galaxies simply trace where the dark matter is densest. The voids, then, are regions where even dark matter is sparse. Imagine trying to map a city at night, but you can only see the streetlights, not the streets themselves. The pattern of lights would show you where the roads are, but you'd be seeing an incomplete picture. That's what we're doing when we map the cosmic web using galaxies. We're seeing the lights, but the underlying structure, the dark matter framework, remains largely invisible. Now here's a common misconception I want to address. When people learn about cosmic voids, they sometimes imagine them as pristine, untouched regions, cosmic wilderness areas that have remained unchanged since the Big Bang. This isn't quite right. The voids are evolving. They're growing. And the few galaxies they do contain are changing in interesting ways. Void galaxies tend to be smaller and bluer than galaxies in dense regions. Blue light comes from hot young stars, which means these galaxies are actively forming new stars. This is somewhat counterintuitive. You might expect that galaxies in crowded neighborhoods where there's more gas and more gravitational interactions would form stars more rapidly. But the opposite is often true. In dense environments, galaxies collide and merge frequently. These violent interactions can actually shut down star formation by heating the gas too much or stripping it away entirely. In the peaceful isolation of the voids, galaxies can form stars at a steady, gentle pace, undisturbed by their neighbors. A team led by astronomer Paul Sutter has been studying void galaxies for years, and they've found some fascinating patterns. Void galaxies rotate more rapidly than their counterparts in dense regions. They're more likely to be spiral galaxies rather than ellipticals. They seem in many ways younger, not in terms of when they formed, but in terms of their evolutionary state. They're like villages that developed slowly and peacefully, while their urban cousins grew quickly through conflict and merger. The discovery of the cosmic web and its voids fundamentally changed how we think about cosmology. Before the surveys of the 70s and 80s, the universe was thought to be relatively simple on large scales. Now we know it's anything but. It's structured, dynamic, evolving in complex ways that we're still working to understand. And here's what strikes me as almost poetic about this discovery. The largest structures in the universe were revealed through patience and systematic observation. Kirshner-Geller-Hutra and their colleagues didn't make their discoveries with a single dramatic observation. They did it through years of careful, methodical work, night after night, galaxy after galaxy, data point after data point. They built maps. They looked for patterns. They trusted that the universe, if observed carefully enough, would reveal its secrets. There's a lesson here that extends beyond astronomy. Sometimes the most profound truths aren't discovered in moments of sudden insight, but through sustained, patient attention. Through showing up, night after night, doing the work, building the picture piece by piece. The cosmic web didn't reveal itself all at once. It emerged gradually as the evidence accumulated. Have you ever had an experience where something you thought was random turned out to have a hidden pattern? Where chaos revealed itself to be order once you looked at it from the right perspective? That's what happened with the distribution of galaxies. What seemed like a random scatter was actually a magnificent architecture, the largest structure in existence. The Bode's void is still there, of course, still mostly empty, still puzzling. Modern surveys have confirmed it's even emptier than Kirshner's team initially thought. With better telescopes and more sensitive instruments, astronomers have found not more galaxies filling in the gap, but rather confirmation of how unusually devoid of matter this region truly is. And it's not alone. The local void, which we exist on the edge of, is about 150 million light-years across. The giant void in Cain's Venatici is larger still, about 1.5 billion light-years in diameter. These aren't rare anomalies. They're the dominant feature of the cosmic landscape. In fact, if you could somehow step outside our universe and look at it from the outside, which you can't, but imagine it, you wouldn't see a scattering of galaxies. You'd see a foam, a web, a sponge. You'd see thin filaments and walls of matter surrounding enormous empty bubbles. You'd see structure, architecture, design in a sense, though not design by any intelligence, just the natural result of gravity and expansion acting over billions of years. The astronomers who mapped this structure didn't just discover where galaxies are. They discovered where galaxies aren't. They learned to read the empty spaces, to see the silence as part of the song. In doing so, they revealed the true shape of the cosmos. As we drift through these thoughts, feeling the weight of cosmic scale settling over us like a soft blanket, we're ready to look even more closely at this architecture. Because the cosmic web isn't just a static picture, it's a dynamic living structure. The filaments flow, the voids expand, the galaxies dance along invisible threads of dark matter. And understanding how this intricate web works, how its pieces fit together and influence each other, brings us one step closer to understanding the universe itself. The structure we've discovered is beautiful in its complexity, ordered in ways that continue to surprise us. Close your eyes for a moment and imagine you're holding the entire observable universe in your hands, not as a sphere of stars, but as a map, a three-dimensional blueprint showing where every galaxy lives. What shape would you see? Until the 1980s, most scientists would have said a cloud. A fairly uniform distribution maybe with some clumps here and there, but overall homogeneous, like grains of sand scattered across a beach. They were wrong. What you'd actually see in your hands would look nothing like a cloud. It would look like a web, or foam, or a sponge. A delicate, intricate structure of threads and sheets and nodes, all surrounding vast, empty chambers. You'd be holding the most complex architecture in existence. If this journey through cosmic structure is resonating with you, I'd be grateful if you'd like this video and subscribe to the channel. These explorations take time to craft, and your support helps us continue creating them. Thank you for drifting through these mysteries with me. The cosmic web. It's one of the most beautiful terms in astronomy, and it describes something even more beautiful, the actual large-scale structure of the universe. Not metaphorically beautiful, literally beautiful. When scientists create three-dimensional maps of galaxy distributions and project them onto a screen, people who've never studied astronomy gasp. It looks like art, like something designed, like the neural networks in a brain, or the mycelium networks beneath a forest floor, or the blood vessels in your body. And yet, it formed naturally through nothing but gravity expansion and time. Let me describe the architecture to you in detail, because understanding its components helps us grasp why the voids are so important. The cosmic web has four main features: filaments, walls, nodes, and voids. The filaments are like cosmic highways, long, thin streams of galaxies that stretch for hundreds of millions of light years. They're not solid structures, but rather concentrations of dark matter, along which galaxies flow like cars on a freeway. If you could watch a time lapse of the universe over billions of years, you'd see galaxies sliding along these filaments, pulled by gravity, gradually accumulating at the intersections. The walls, sometimes called sheets or planes, are two-dimensional surfaces where galaxies cluster together. Think of them as the films in soap bubbles. They're extremely thin compared to their width and length, sometimes only a few million light years thick, but hundreds of millions of light years across. The Great Wall that Geller and Hucre discovered in 1989 is one of these structures, a vast sheet of galaxies separating even vaster voids. The nodes are where multiple filaments intersect. These are the richest galaxy clusters, places like the Coma cluster or the Virgo cluster, where thousands of galaxies crowd together in a relatively small volume of space. They're the cities of the cosmic web, the bright lights at the major intersections. And then there are the voids, the empty chambers surrounded by this network of matter. They're not perfectly spherical, but they're approximately so. They're not perfectly empty, but they're close. And they make up the majority of the volume. Now here's what makes this structure so remarkable. It emerged from an almost completely uniform starting state. In the first few 100,000 years after the Big Bang, matter was distributed extraordinarily evenly throughout space. The temperature and density varied by less than 1 part in 100,000 from place to place. If you could have taken a snapshot of the universe at that time, it would have looked perfectly boring, a uniform fog of hydrogen and helium with tiny, almost imperceptible fluctuations. But those tiny fluctuations were enough. They were quantum fluctuations imprinted during the inflationary period in the first fraction of a second after the Big Bang. And as the universe expanded and cooled, gravity amplified them. In regions that were even slightly denser than average gravity, pulled in more matter, making them denser still. In regions that were even slightly less dense than average matter, was pulled away, making them sparser still. This process, called gravitational instability, created a feedback loop that amplified small differences into enormous structures. The Millennium simulation I mentioned earlier demonstrates this beautifully. It starts with a nearly uniform distribution of dark matter particles, adds the expansion of the universe and the force of gravity, and then lets the simulation run forward in time. No special rules, no artificial intervention, just physics. And what emerges after billions of simulated years is the cosmic web. Filaments form naturally. Walls develop as filaments intersect. Nodes appear where multiple walls meet, and voids, those vast empty regions, arise in the spaces between. When scientists compare the output of this simulation to actual maps of the universe, the match is stunning. The computer-generated cosmic web looks almost identical to the real one. This tells us something profound. We understand the basic physics that created the large-scale structure of the universe. Gravity plus expansion plus tiny initial fluctuations equals the cosmic web. But understanding how something formed doesn't mean we understand everything about it. The cosmic web has properties that continue to surprise us. For example, the filaments aren't static. Galaxies flow along them, falling toward the nodes. A team of astronomers led by Noam Libeskind calculated these flow patterns in 2015, and they found that galaxies are streaming through space at hundreds of kilometers per second, following the invisible architecture of dark matter. Our own Milky Way is part of this flow. We're moving through space at about 600 kilometers per second, relative to the cosmic microwave background, not because of the expansion of the universe, but because we're being pulled along a filament toward a massive structure called the Shapley supercluster, which lies about 650 million light-years away. Think about that. Everything you've ever known, Earth, the solar system, every star you can see in the night sky, all of it is falling through space at more than 2 million kilometers per hour, following the gravitational currents of the cosmic web. And you can't feel it because we're all moving together, carried by the same current. The walls, too, are dynamic. They're not rigid barriers, but fluid structures constantly evolving as galaxies are born, merge, and die. Some walls are rich in gas, visible in X-ray telescopes as filaments of hot plasma. Others are mostly dark matter, revealed only by their gravitational effects on light passing through them. Scientists have discovered that the walls between voids aren't uniform in thickness. Some sections are thin and fragile, while others are thick and robust. And where walls are thin, occasionally a void will break through, merging with a neighboring void to create an even larger empty region. The voids themselves are growing, expanding, consuming the space around them. Let me share a comparison that helps illustrate the scale and structure of the cosmic web. Imagine you're an ant living on a vast sponge, the kind used for washing dishes with lots of holes and chambers. To you, the solid parts of the sponge would seem like an entire world, chambers and tunnels and walls extending in every direction. You might spend your whole life exploring these solid regions without ever realizing that most of the sponge is actually empty space. That's our situation. We live in the solid part of the cosmic sponge, in a galaxy in a filament near a wall. We're surrounded by matter, but most of the sponge, most of the universe, is void. Now, one of the most fascinating aspects of the cosmic web is its self-similarity across scales. This is a mathematical property called fractality. The cosmic web looks similar, whether you zoom in or zoom out, like a fractal pattern. At the smallest scales, we can observe galaxies cluster together. Zoom out, and you see these clusters connected by filaments. Zoom out further, and you see the filaments are part of superclusters. Zoom out even more, and you see the superclusters form even larger walls and filaments. At every scale, the pattern repeats, matter concentrated along interconnected structures with voids in between. This self-similarity isn't perfect. There are limits to the scale of structures, but it's remarkably consistent, and it emerges naturally from the physics of gravitational collapse. No designer needed, no planning required, just the same simple rules applied at every scale, producing complexity through repetition. But here's where our understanding gets truly interesting. The cosmic web isn't made of galaxies. It's made of dark matter. Dark matter makes up about 85% of all the matter in the universe. We can't see it directly because it doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational effects. When we map the cosmic web using galaxies, we're actually mapping the skeleton underneath the framework of dark matter that formed first, and along which normal matter later accumulated to form stars and galaxies. Imagine trying to understand the structure of a building at night, when you can only see the windows that are lit. You'd get an idea of the building's shape, but you'd be missing most of the structure, the walls, the floors, the framework that holds everything together. That's what we're doing when we map the cosmic web with galaxies. The galaxies are the lit windows. The dark matter is the building. Scientists have developed techniques to map dark matter directly using something called gravitational lensing. When light from distant galaxies passes through regions of space with lots of dark matter, the gravity bends the light, distorting the images we see. By carefully analyzing these distortions, astronomers can create maps of where dark matter is concentrated. And what these maps reveal is extraordinary. The cosmic web of dark matter is even more pronounced, even more structured than the web of visible matter. The filaments are thinner and denser. The voids are emptier. The dark matter web is like the underlying blueprint, and the galaxies we see are just decorations hung upon it. There's a research team in the Netherlands, led by Rian van de Weijgaert, that has spent decades studying the geometry and topology of the cosmic web. They've developed mathematical tools to classify and measure different types of structures to distinguish between filaments and walls, to measure void sizes, to track how the web evolves over time. Their work has revealed something profound. The cosmic web isn't random. It is preferred orientations, preferred scales, patterns that repeat. It's not chaos. It's ordered complexity, the kind of pattern that emerges when simple rules are applied consistently over cosmic timescales. And the voids, they're integral to this pattern. They're not just gaps between structures. They're structural elements themselves. The voids define the web as much as the filaments do. You can't have one without the other. Think of it this way. In architecture, the spaces between walls, the rooms, the hallways are as important as the walls themselves. A building is defined by both its solid elements and its empty spaces. Remove either, and you no longer have functional architecture. The same is true for the cosmic web. The voids aren't just leftover space. They're part of the design. There's another layer to this that I find particularly moving. The cosmic web connects everything. Every galaxy in the universe is part of this vast network. Matter flows along it. Information in the form of gravitational waves, cosmic rays, stray atoms, travels along its pathways. In a very real sense, the cosmic web is the circulatory system of the universe, and we're part of it. Every atom in your body was once part of this network. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was forged in stars that were themselves embedded in the cosmic web, connected to everything else through invisible threads of gravity and space. You are not separate from the universe. You are woven into its structure. Now I want to address a common misunderstanding about the cosmic web. Sometimes people hear about these vast structures and imagine that the universe has hard boundaries, that there are walls you could run into, like the walls of a room. This isn't correct. The walls and filaments of the cosmic web are regions of higher galaxy density, not solid barriers. If you were in a spaceship traveling through a cosmic wall, you wouldn't hit anything. You'd simply notice that galaxies were more densely packed around you. The web is statistical, not physical. Similarly, the voids aren't absolutely empty. They contain some galaxies, just far fewer than the walls and filaments. They contain dark matter, just much less of it. They contain gas, though it's extremely diffuse. The void isn't a vacuum in the absolute sense. It's a relative emptiness, a region where the density of matter is far below average. But that relative emptiness has real effects. Galaxies and voids evolve differently. The expansion of space proceeds differently. Even the passage of time might be subtly different, though that's still being researched. As you rest here, breathing slowly, feeling the stillness of this moment, consider that you exist within this cosmic architecture. Not metaphorically, but literally. The web surrounds you. Its currents flow through you. Its history is written in every atom of your being. And understanding this doesn't diminish you. It connects you to something vast and ancient and ongoing. The cosmic web reminds us that structure emerges from simplicity, that complexity doesn't require design, that beauty can arise from basic physical laws applied consistently over time. It's a lesson that applies to so much beyond cosmology, to life, to consciousness, to the patterns that emerge in our own existence when we pay attention to them. But the cosmic web doesn't just exist, it acts. The voids push, the filaments pull, the nodes attract. This intricate architecture isn't passive scenery, it's a dynamic system that shapes the evolution of everything within it, including the galaxies themselves. And as we're about to discover, the emptiness at the heart of the voids may be the most active force of all. Here's something that might change how you think about power and influence. We usually assume that to affect something, you need to be present. To move something, you need to touch it. To change something, you need to interact with it directly. But what if absence could be just as powerful as presence? What if emptiness could shape reality as profoundly as matter? What if nothing could do something? The cosmic voids prove that it can. And understanding how they do it reveals one of the most elegant principles in the universe. If these ideas are stirring something in you, I'd love it if you'd take a moment to like this video and subscribe. Your engagement truly helps these explorations reach others who are searching for the same sense of wonder and peace in the cosmos. Thank you for being part of this journey. Let's start with a fundamental question. If the voids are mostly empty, why do they matter? Why should we care about regions of space where almost nothing happens? The answer is beautifully counterintuitive. The voids matter precisely because they're empty. Their emptiness gives them power. To understand this, we need to think about how gravity works on cosmic scales. We're used to thinking of gravity as an attractive force, planets pulling on moons, stars pulling on planets, galaxies pulling on stars. And that's correct. Gravity attracts matter to matter. But here's what's less obvious. In a region with very little matter, gravity has very little to pull with. And when gravity is weak, other forces like the expansion of space itself become dominant. This is what happens in the voids. With so little matter inside them, their gravity is too weak to hold things together. Instead, the expansion of the universe takes over. The voids expand, and as they expand, they push matter away from their centers toward their boundaries, toward the filaments and walls we discussed earlier. Think of it like this. Imagine a bubble forming underwater. As it grows, it doesn't just get bigger, it actively pushes water away from its surface. The voids work similarly. They're not passive empty spaces. They're actively growing regions that push galaxies outward. This was first proposed theoretically in the 1980s, but it wasn't confirmed observationally until the 2000s, when astronomers developed techniques to measure the velocities of galaxies near void boundaries. A team led by Rien van de Weigert published a landmark study in 2008, showing that galaxies do indeed flow away from void centers at speeds of several hundred kilometers per second. Several hundred kilometers per second. Think about that scale. If you were somehow standing at the center of a void and could see the nearest galaxies which you couldn't, they'd be too far away. You'd observe them all receding from you at speeds that dwarf anything we experience in daily life. The fastest human-made object, the Parker Solar Probe, travels at about 200 kilometers per second at its maximum speed. The galaxies fleeing from void centers are moving even faster than that. But the void effect isn't just about motion. It's about transformation. Galaxies that live in voids are fundamentally different from galaxies that live in dense regions. And studying these differences has taught us profound lessons about how environment shapes evolution, not just for galaxies, but as a principle that applies throughout nature. Let me introduce you to void galaxies. They're fascinating creatures. First void galaxies tend to be smaller than their counterparts in dense regions. The median mass of a void galaxy is about 60 to 70% of the median mass for galaxies in filaments or clusters. Why? Because in the voids, there's less matter available to build galaxies, and there are fewer opportunities for galaxies to grow by merging with the neighbors. Second void. Galaxies are bluer. In astronomy, blue means young hot stars, which means active star formation. Galaxies in voids are still making new stars at a steady rate, while many galaxies in dense regions have stopped forming stars altogether. This is counterintuitive. You'd think that in crowded regions, where there's more gas and more gravitational interactions, star formation would be more vigorous. But the opposite is often true. In dense environments, galaxy collisions and mergers can heat gas to such high temperatures that it can't cool down and collapse to form stars. Or the gas gets stripped away entirely by interactions with the hot plasma that fills galaxy clusters. In the peaceful isolation of the voids, galaxies can form stars at a steady, gentle pace. They're not disrupted by violent collisions. They're not having their gas stolen by neighbors. They're just quietly making stars, year after year, billion after billion years. A researcher named Paul Sutter has dedicated much of his career to studying void galaxies. In a 2012 paper, he and his colleagues analyzed thousands of galaxies in and around voids, and they found something remarkable. Void galaxies aren't just different in mass and color. Their shapes are different too. Void galaxies are more likely to be spiral galaxies, elegant disks with graceful arms, rather than elliptical galaxies, which are more round and featureless. This makes sense when you think about it. Spiral galaxies are fragile structures. If you collide two spiral galaxies, they merge into an elliptical. But in the voids, collisions are rare. Spirals can maintain their delicate architecture for billions of years. There's something poignant about this. In the emptiest regions of space, where one might expect nothing but desolation, there's actually a kind of preservation. The voids protect their residents from the chaos that reigns in denser neighborhoods. They're cosmic nature preserves, in a sense places where galaxies can evolve slowly and peacefully. But the void effect goes deeper than just affecting individual galaxies. The voids shape the flow of matter through the entire cosmic web. Imagine you're tracing the life story of a cloud of gas in the early universe. Shortly after the Big Bang, this cloud is part of the fairly uniform distribution of matter. But as structure begins to form, the cloud finds itself in a region that will become a void. As the void expands, the cloud gets pushed outward along with everything else in that region. Eventually, the cloud reaches the boundary of the void, the edge where the emptiness meets the filaments. Here, it encounters a very different environment. Density is higher. Gravity is stronger. The cloud gets compressed by the infalling matter from all directions, and in this compression conditions become right for star formation. The cloud collapses. A galaxy is born, not in the void itself, but at its boundary, where the pushing force of the void's expansion meets the pulling force of the filament's gravity. This is why the walls between voids are such active regions. They're where opposing forces meet. They're where matter piles up. They're galaxy formation hotspots. A study published in 2015 by Yehuda Hoffman and his team used computer simulations to track this process in detail. They found that the voids act like cosmic shepherds herding matter toward the filaments and walls. Without the voids, without their expansive push, the cosmic web would look very different, more uniform, less structured. The voids are what create the sharp contrasts we observe. Here's another way to think about it. The voids are like the negative space in a sculpture. A skilled sculptor doesn't just carve the figure. They carve the space around the figure too, because that's what defines it. The voids are the negative space of the universe. They define the structure by being absent. But there's something even more profound happening in the voids, something that takes us to the frontier of cosmology. The voids might be the key to understanding dark energy. Dark energy is the mysterious force causing the expansion of the universe to accelerate. It makes up about 68% of the total energy content of the cosmos. We know it exists because we can measure its effects, but we don't know what it is. We don't know why it exists. We don't even know if it's truly a form of energy, or if it's something else entirely, perhaps a property of space itself, or a sign that our understanding of gravity breaks down on cosmic scales. The voids are the perfect laboratories for studying dark energy, because in the voids, dark energy dominates. There's so little matter that gravity is weak, and the accelerating expansion becomes the primary force at work. Think of it this way. In dense regions like galaxy clusters, gravity is strong enough to overcome the expansion of space. The cluster stays bound together, even as the universe expands around it. But in the voids where gravity is weak, space expands freely. The voids are where we can see dark energy at work, most clearly unmasked by the complications of matter. Researchers have proposed using the expansion rates of voids as cosmic rulers tools for measuring how dark energy has changed over time. If dark energy is truly constant, as Einstein's cosmological constant would suggest, then voids should expand at predictable rates. But if dark energy varies over time, as some alternative theories propose, then void expansion rates should show corresponding variations. A team led by Seshadri Nadathar published results in 2019 showing that measuring void properties can indeed constrain dark energy models. Their work suggested that studying voids might help resolve some of the tensions in current cosmology disagreements about the expansion rate of the universe that arise when we measure it in different ways. The voids also teach us about feedback, about how systems regulate themselves through cycles of cause and effect. As a void expands, it becomes emptier, which weakens its gravity, which allows it to expand faster, which makes it emptier still. It's a positive feedback loop, a runaway process that amplifies small differences into large ones. This kind of feedback is ubiquitous in nature. In climate science, it explains ice ages more. Ice reflects more sunlight, which causes more cooling, which causes more ice. In economics, it explains market crashes. Falling prices cause selling, which causes prices to fall more, which causes more selling. In ecology, it explains extinction cascades. Losing one species affects others, which affects still others in an amplifying chain. The voids show us this principle operating on the largest scales imaginable. They demonstrate that in complex systems, small differences can grow into enormous structures through feedback processes operating over long periods of time. Have you ever experienced how absence can be more powerful than presence? How silence can be louder than noise? How the space between words can carry more meaning than the words themselves? The voids embody this principle cosmically. Their absence is their power. Their emptiness is their influence. There's also a lesson here about perspective. For most of human history, we thought the universe was full of stars, full of galaxies, full of matter. We focused on what was there. But as we've learned more, we've discovered that most of the universe is what's not there. Most of it is empty space, dark matter. We can't see dark energy. We don't understand. The voids remind us that reality is often the opposite of what we assume, that the important things aren't always the obvious things, that what seems absent might be the most present force of all. Scientists studying void galaxies have also discovered something unexpected about galactic rotation. Void galaxies spin faster than galaxies in dense regions. A study by Ricarda Stark and her colleagues in 2016 found that void galaxies have, on average, 20% higher rotation speeds than field galaxies. Why would this be? The leading hypothesis is that void galaxies experience fewer tidal interactions, fewer gravitational tugs from passing neighbors that would slow their rotation over time. In the isolation of the voids, they maintain their primordial spin. It's like the difference between a figure skater spinning alone on ice versus in a crowded rink where people keep bumping into them. In the void, galaxies can spin freely, unimpeded. This has implications for how we understand galaxy evolution. It suggests that much of what we observe in dense regions, the galaxy types, the star formation rates, the merger histories is shaped by environment. The default state of a galaxy, the way it would evolve if left completely alone, is better represented by void galaxies than by galaxies in clusters. The voids are showing us what galaxies are like when environment doesn't interfere. They're cosmic control groups in the grand experiment of galaxy formation. There's something humbling about realizing that the places we've studied most intensely, the galaxy clusters, the rich groups, the dense filaments, are actually the exceptional cases. The voids, which we've only recently begun to study seriously, represent the norm. Most of the universe's volume is void-like. Most of the universe is empty and quiet. And in that emptiness, in that quiet, profound things happen. Galaxies form at the boundaries. Matter flows along invisible currents. Space itself expands, revealing the mysterious force we call dark energy. The voids aren't inactive. They're engines of cosmic evolution, working slowly and invisibly to shape everything around them. As you rest in this moment, breathing gently, perhaps you can sense a parallel in your own experience. The quiet moments in your life, the pauses, the rests, the empty spaces in your schedule. These aren't wasted time. They're when integration happens, when healing occurs, when clarity emerges. The void in your day might be as important as the void in the cosmos, a place where the usual forces are suspended and different possibilities arise. The voids have shown us that emptiness is not passive, that absence has agency, that nothing is something. But there's one more surprise waiting for us in this exploration of cosmic architecture. Because it turns out we're not just observing the voids from a distance, we're living in one. Our home, our galaxy, our local group of galaxies. All of it sits on the edge of a vast, empty region. And this fact, this cosmic address, has profound implications for everything we observe and everything we think we understand about the universe. What if I told you that every observation you've ever made of the universe, every measurement of cosmic expansion, every calculation of galaxy distances, every assumption about what's normal in the cosmos has been influenced by where you happen to be standing? And what if where you happen to be standing is one of the least typical places in the entire universe? What if we're living on the edge of emptiness, looking out from the boundary of a vast cosmic void? This isn't speculation. It's fact. And when astronomers discovered it in the 1980s, it fundamentally changed how we interpret everything we observe about the cosmos. If this revelation is resonating with you, this sense that our cosmic address shapes our cosmic perspective, I'd be grateful if you'd like this video and subscribe to the channel. These stories take time to research and craft, and your support helps us continue exploring the mysteries that connect us to the universe. Thank you. The story begins in 1987, though its roots stretch back several years earlier. An astronomer named Brent Tully, working at the Institute for Astronomy in Hawaii, was doing something that had become his specialty, mapping the three-dimensional positions of nearby galaxies. Tully had developed a method for measuring galaxy distances that was more accurate than previous techniques. He could determine not just which direction a galaxy was in, but how far away it was. And as he mapped more and more galaxies in our local region of the universe, within about 300 million light-years of the Milky Way, he noticed something odd. There was a large region with very few galaxies, and we were right next to it. He called it the local void. The name was deliberately understated, almost casual, but what it represented was profound. We live in a cosmic suburb perched on the edge of a nearly empty region, about 150 million light-years across. Think about that for a moment. 150 million light-years. If you could somehow travel at light speed from one side of the local void to the other, human civilization would rise and fall 7,500 times before you reached the other side. The entire history of agriculture, writing cities, nations, technology, all of it is just 0.02 of 1% of that journey. And this void is our neighbor. We live right on its edge, looking into it, like someone living in a house at the edge of a vast desert. When Tully published his findings, the astronomical community had to grapple with an uncomfortable question. How much of what we think we know about the universe is actually just what we know about our particular neighborhood? How typical is our location? The answer, it turns out, is not very typical at all. Let me give you some context. The Milky Way is part of a small group of galaxies called, rather unimaginatively, the local group. This includes Andromeda, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. The entire local group spans about 10 million light-years. The local group, in turn, is part of a larger structure called the Virgo supercluster, which contains thousands of galaxy groups and clusters spread across about 110 million light-years. We're on the outer edge of this supercluster, and the Virgo supercluster itself sits on the boundary between the local void and denser regions of space. We're literally perched on the edge of emptiness, looking outward toward where the galaxies are. This has consequences, real measurable consequences for how we observe the universe. For one thing, our velocity through space is influenced by our location. The Milky Way is moving at about 600 kilometers per second relative to the cosmic microwave background. Part of this motion is due to gravitational attraction from the Virgo cluster and other dense structures ahead of us, but part of it, a significant part, is due to the local void pushing us away. Wait, pushing us away? Yes. Remember what we learned about the void effect. Voids expand, and as they expand, they push matter away from their centers. The local void is pushing us along with the rest of the local group away from its center and toward denser regions of space. This was confirmed dramatically in 2017 when a team led by Yehuda Hoffman published a landmark study identifying what they called the dipole repeller, a region of space that's repelling us as much as the dense structures ahead of us are attracting us. And where is this repeller? It's the local void. Think of it like being on a playground seesaw. On one end, dense structures like the Virgo cluster are pulling us toward them through gravity. On the other end, the local void is pushing us away through its expansion. Both forces shape our motion through space. This discovery resolved a long-standing puzzle in cosmology. Scientists had known for decades that the Milky Way was moving toward the Virgo cluster at about 200 kilometers per second. But calculations showed that the Virgo cluster alone wasn't massive enough to account for all our motion. something else had to be contributing. That something else was the local void pushing from behind. But the implications go much deeper than just our motion. Our location on the edge of a void affects what we see when we look out into the universe. Imagine you're trying to measure the average density of population in your country, but you happen to live in a rural area. If you only measure the density in your immediate surroundings, you'll underestimate the national average. You need to account for the fact that you're in an atypical location. The same principle applies to cosmic observations. When we measure the local expansion rate of the universe, what's called the Hubble constant, we're measuring it from within a region that's less dense than average. The local void's expansion influences the expansion we observe nearby. If we don't account for this, we might calculate the wrong value for the Hubble constant. And here's where things get interesting. There is currently a major disagreement in cosmology about the value of the Hubble constant. Measurements made using nearby supernovae give one value. Measurements made using the cosmic microwave background, the afterglow of the Big Bang observed from billions of light years away, give a different value. The discrepancy is about 10%, which doesn't sound like much, but in precision cosmology, it's huge. It's called the Hubble tension. Could our location in the local void be contributing to this tension? Some researchers think so. A study published in 2020 by Benjamin Hoshett and Amy Barger suggested that accounting for the local void's effects could reduce, though not eliminate, the Hubble tension. The jury is still out on this. The Hubble tension might have other causes. Perhaps our understanding of dark energy is incomplete, or perhaps there's some systematic error in how we're measuring distances. But a fact that we live next to a void is definitely a factor that needs to be considered. This raises a profound philosophical question that astronomers don't often discuss openly. How much of cosmology is really cosmology, the study of the universe as a whole, versus topology, the study of our particular place in the universe? When we measure cosmic expansion, when we study the distribution of galaxies, when we analyze the properties of the cosmic web, we're always doing it from here, from this particular location, from the edge of the local void, and that colors everything we observe. It's similar to a problem that philosophers call the observer selection effect. The very fact that we exist to observe the universe means we must be in a location where conditions permit observers to exist. We couldn't observe the universe from inside a black hole or from the center of a void where no galaxies form. By necessity, we observe from a place atypical enough to support complex structures like galaxies, stars, and planets. But there's another layer to this. The local void isn't just affecting our measurements, it's part of our history. Our cosmic address has shaped the evolution of our galaxy and our local group. Because we're on the edge of a void, we're in a region of moderate density, not as dense as a galaxy cluster, where collisions and mergers are frequent and violent, not as sparse as the interior of a void, where galaxies are isolated and resources are scarce. We're in a Goldilocks zone, not too dense, not too sparse, but just right. This moderate density environment may have been crucial for the development of life. In very dense regions, high-energy events like supernovae and gamma-ray bursts are more frequent, potentially sterilizing planets with radiation. In very sparse regions, there may not be enough heavy elements, the carbon, oxygen, nitrogen, and other elements forged in stars to build complex chemistry and life. On the edge of a void, we get the benefits of being near enough to other galaxies for occasional interactions and enrichment, but far enough away to avoid the most violent processes. It's a sweet spot. Have you ever felt like your environment shapes who you are in ways you don't consciously notice? That where you grew up, where you live now, influences your perspective more than you realize. The local void is our cosmic environment, and it's been shaping us and our ancestors and the stars that made them and the galaxy that made those stars for billions of years. The discovery of the local void also taught astronomers an important methodological lesson. You can't assume your local environment is representative of the whole. This seems obvious when stated baldly, but in practice, it's easy to forget. Throughout the history of science, researchers have repeatedly made the mistake of generalizing from their immediate experience. For centuries, Europeans believed the world's climate was temperate because that's what they experienced in Europe. For decades, astronomers believed all galaxies were spiral or elliptical because those were the types they saw most clearly nearby. Time and again, broader sampling has revealed that the local case was special, not typical. The local void is a cosmic scale reminder of this principle. We don't live in an average part of the universe. We live in a specific place with specific properties, and understanding those properties, understanding our cosmic address, is essential for interpreting our observations correctly. Let me share another fascinating detail about the local void. Its existence was actually predicted before it was discovered. In the early 1980s, astronomers noticed that galaxies in our local region showed a peculiar pattern in their velocities. They seemed to be flowing away from a particular region of space. This suggested there must be an underdense region, a void, pushing them. When Tully mapped the galaxy distribution in 3 dimensions, he confirmed this prediction. The void was real. This is how science works. At its best, observations suggest a hypothesis. Predictions are made, and then direct measurements confirm or refute those predictions. The local void went from theory to fact. But here's something that still puzzles astronomers. The local void is not perfectly empty. Like all voids, it contains some galaxies about 60% fewer than you'd expect in a typical region of space of the same size. Where did these void galaxies come from? Were they born in the void? Or did they fall in from the edges after the void formed? Studies suggest a mix of both. Some void galaxies appear to be true natives they formed in place from the small amount of matter that remained as the void expanded. Others show signs of having migrated inward, perhaps falling along minor filaments that thread through even the emptiest regions. These local void galaxies are laboratories for studying how isolation affects galactic evolution. There are nearest examples of void dwellers close enough to observe in detail, and they show the same characteristics we discussed earlier. They're smaller, bluer, more actively forming stars than galaxies in denser environments. One particularly interesting local void galaxy is NGC 3109. A small, irregular galaxy about 4 million light-years away from us. It's forming stars vigorously, despite being quite isolated. Studies of galaxies like NGC 3109 help astronomers understand what galaxies are like when they evolve in peace, without the constant harassment of neighbors. The local void has also become a testing ground for cosmological theories. Because it's nearby and well studied, astronomers can compare detailed observations of its properties with detailed predictions from computer simulations. Does the local void expand at the rate predicted by our models of dark energy? Do galaxies flow away from its center at the expected velocities? Are its boundaries as sharp or as fuzzy as simulations suggest? So far, the local void matches theoretical expectations remarkably well. This is reassuring. It suggests our models of cosmic structure formation are on the right track, but there are still discrepancies, still puzzles, still questions that keep researchers up at night. For instance, the local void seems to be slightly elongated rather than perfectly spherical. Why is this just random chance, or does it tell us something about how voids form and evolve? And how does the local void connect to other nearby voids? Is it an isolated bubble or part of a larger network of interconnected empty regions? These might seem like obscure technical questions, but they matter because they're about understanding the architecture of our cosmic neighborhood. They're about knowing where we live. And increasingly, astronomers are realizing that where we live extends far beyond the local void. Recent studies have mapped our position within an even larger structure called the Laniakea supercluster, a collection of galaxies spanning 500 million light-years, with the local void forming one of the boundaries within it. Laniakea means immense heaven in Hawaiian, and it's an appropriate name. This is our true cosmic address. The Milky Way galaxy in the local group on the edge of the Virgo supercluster, bordering the local void within the Laniakea supercluster itself, part of an even larger structure of filaments and voids extending billions of light years. Each level of this address matters. Each scale influences our motion, our observations, our history. We are nested within structures, and the local void is one of the most important of these nesting levels, the one that most directly shapes our immediate cosmic environment. As you rest here, breathing softly, consider this strange fact: you live on the edge of nothing. The place you call home, this planet, this solar system, this galaxy, sits on the boundary of vast emptiness. Behind us, if we look in the right direction, there's a hole in space, 150 million light-years wide, and this location, this cosmic address on the edge of the void, has shaped everything about our existence. It influences how fast we move through space. It affects what we see when we look outward. It may have provided the balanced environment necessary for complex structures, like solar systems, and life to develop. We are void edge dwellers. It's part of our identity, cosmically speaking. And understanding this fact, really grasping what it means to live where we live, changes how we think about our place in the cosmos. But the local void is just one piece of a much larger puzzle, because spread throughout the universe in numbers we're still trying to count, there are other voids, hundreds of them, thousands, maybe millions. And some of these voids are hiding one of the greatest mysteries in all of cosmology, a puzzle that connects the earliest moments after the Big Bang to the fundamental nature of the cosmos itself. Imagine discovering that the universe is not just expanding, but accelerating, speeding up as it grows, that everything is flying apart faster and faster, driven by some mysterious force that fills all of space, but that we cannot see, cannot touch, cannot understand. Now imagine that the best place to study this force, this dark energy that makes up most of the universe, is in the emptiest regions of space, in the voids, in the nothing. This is where we are in cosmology right now, standing at the edge of one of the greatest mysteries in science and finding that the answer might be hiding in plain sight in the places we once thought were unimportant. If these cosmic mysteries are speaking to something in you, this sense of wonder mixed with humility, I'd be honored if you'd like this video and subscribe. These journeys through the unknown are made possible by your support and presence. Thank you for being here, seeking understanding alongside me. Let me take you back to 1998. Two teams of astronomers working independently were studying distant supernovae exploding stars that serve as cosmic distance markers. They expected to find that the universe's expansion was slowing down, gradually decelerated by the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The universe's expansion was speeding up. This discovery was so shocking, so contrary to expectations, that both teams checked their data repeatedly. They looked for errors in their measurements. They questioned their assumptions. They wondered if their instruments were faulty. But the evidence kept pointing to the same conclusion. Something was pushing the universe apart, overcoming gravity, causing the expansion to accelerate. The leaders of these teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, would later win the Nobel Prize in Physics for this discovery. But at the time, they were simply bewildered. What could possibly be causing this acceleration? The answer, or at least the name for it, came from an old idea proposed by Albert Einstein 8 decades earlier. In 1917, Einstein added a term to his equations of general relativity, a cosmological constant represented by the Greek letter lambda. He added it because he thought the universe was static, neither expanding nor contracting, and he needed something to balance gravity's tendency to pull everything together. When Edwin Hubble discovered in 1929 that the universe was actually expanding, Einstein famously called the cosmological constant his biggest blunder. He removed it from his equations. But now, 70 years later, the universe was telling us that Einstein's blunder might not have been a blunder after all. The cosmological constant, or something very much like it was real, and it was the dominant form of energy in the universe. Scientists called it dark energy. Not because it's dark in the sense of blocking light, but because we don't know what it is. It's mysterious, hidden, invisible, except through its effects on cosmic expansion. Current measurements suggest that dark energy makes up approximately 68% of the total energy content of the universe. Dark matter, the invisible matter that provides the gravitational scaffolding for the cosmic web, makes up about 27%. Normal matter, the stuff that makes up stars and planets and people, is only about 5%. We are living in a universe dominated by things we don't understand. And of those things we don't understand, dark energy is the most abundant and the most mysterious. Here's what we know about dark energy. It has a property called negative pressure. In normal matter, pressure pushes things apart like air molecules in a balloon pushing against the balloon's walls. But in Einstein's equations, negative pressure creates a kind of repulsive gravity. Instead of pulling things together, it pushes them apart. Dark energy appears to be spread uniformly throughout space. Unlike matter, which clumps into galaxies and clusters, dark energy has the same density everywhere in the voids, in the filaments, in galaxy clusters, even in the space between atoms in your body. About 0.6 proton masses per cubic meter. That's not much, but space is vast, and it all adds up. As the universe expands, matter gets more dilute, the same amount of matter spread over more volume. But dark energy doesn't dilute. Its density stays constant, even as space expands. This means that as time goes on, dark energy becomes increasingly dominant compared to matter. Early in the universe's history, matter dominated, and the expansion was decelerating. But about 5 billion years ago, dark energy became dominant, and the expansion began to accelerate. 5 billion years ago. That's around the time our solar system was forming. In a very real sense, we live in the age when dark energy took over the universe. Now, here's where the voids become crucial to this story. In dense regions of space, galaxy clusters, for example, gravity from all the matter is strong enough to overcome dark energy locally. The cluster stays bound together, even as the space around it expands. But in the voids, where matter is sparse and gravity is weak, dark energy dominates completely. The voids are expanding at nearly the maximum rate allowed by dark energy, unhindered by significant gravitational resistance. This makes the voids perfect laboratories for studying dark energy. In dense regions, the effects of dark energy are masked by the complexity of gravitational interactions. But in the voids, we can see dark energy at work in its purest form. Think of it like trying to hear a quiet sound in a noisy room versus a silent one. In the galaxy clusters, the noisy room's dark energy signal is drowned out by the loud noise of matter's gravity. But in the voids, the silent room's dark energy's whisper can be clearly heard. Astronomers have developed several techniques to use voids as dark energy probes. One approach pioneered by researchers like Margaret Collis and Paul Sutter involves measuring void sizes at different cosmic epochs, different times in the universe's history. If dark energy is constant, as the cosmological constant model suggests, then voids should expand at predictable rates. But if dark energy changes over time, void sizes would deviate from these predictions. Another technique, called the Alcock-Peksinski test, uses the shapes of voids. If the universe's expansion is accelerating at the rate we think it is, then voids should appear slightly elongated in certain directions due to the geometry of space-time. By measuring thousands of voids and analyzing their shapes statistically, astronomers can constrain the properties of dark energy. A particularly elegant approach involves studying how galaxies fall into voids from the edges. As a void expands, it pulls galaxies inward from its boundaries, or rather the galaxies fall toward the slightly denser walls, while the void center recedes. The velocity of this infall depends on both the gravitational pull of matter on the void's edges and the push of dark energy from within. By measuring these velocities precisely, astronomers can separate the effects of matter and dark energy. A team led by Seshadri Nadathar published results in 2019 using this technique. They analyzed the velocity field around cosmic voids in the Sloan Digital Sky Survey and found that their measurements were consistent with the standard cosmological constant model of dark energy. But the margins of error were still large. We need better data, more precise measurements, larger samples of voids. This is where future surveys come in. The Dark Energy Spectroscopic Instrument, or DESI, which began operations in 2021, will map millions of galaxies and measure the properties of thousands of voids with unprecedented precision. The European Space Agency's Euclid mission, launched in 2023, will do the same, using both spectroscopy and imaging. These surveys should dramatically improve our understanding of how dark energy behaves in voids. But here's the deeper question. What is dark energy really? The cosmological constant model treats it as a property of space itself, a sort of intrinsic energy that every cubic meter of vacuum possesses. In quantum field theory, this is sometimes called vacuum energy. The quantum fields that permeate space have fluctuations even in their lowest energy state, and these fluctuations might manifest as dark energy. There's just one problem with this idea. When physicists calculate how much vacuum energy quantum field theory predicts, they get an answer that's about 10 to the power of 120 times larger than the observed value of dark energy. That's a 1, followed by 120 zeros. It's possibly the worst prediction in the history of physics. This is called the cosmological constant problem, and it's one of the deepest puzzles in theoretical physics. Why is the vacuum energy so much smaller than quantum theory predicts? Why isn't it exactly 0? And why does it happen to have the precise value that allows structures like galaxies to form? Some physicists propose that dark energy isn't constant at all. Perhaps it's a dynamic field called quintessence that changes over time. The name comes from the ancient concept of the fifth element beyond earth, air, fire, and water. Quintessence models allow dark energy's density to vary across space and evolve over cosmic history. Others suggest that dark energy might not exist at all, that what we're observing is actually a breakdown of Einstein's general relativity on cosmic scales. Perhaps gravity works differently over distances of billions of light years than it does in our solar system. These modified gravity theories are controversial, but they can't be ruled out with current data. And then there are even more exotic ideas. Some cosmologists propose that we live in a multiverse, an ensemble of universes with different physical constants. In most of these universes, dark energy is either 0 or enormous, and complex structures can't form. We observe the value we do simply because we couldn't exist in universes with different values. This is called the anthropic principle, and it's philosophically troubling to many physicists because it seems to give up on finding a deeper explanation. The voids might help us distinguish between these possibilities. Different models of dark energy make different predictions about how voids evolve, how their expansion rates change over time, how they interact with surrounding structures. By carefully measuring void properties at different cosmic epochs, we can test which model matches reality. There's something both humbling and exciting about this situation. We've discovered that most of the universe consists of something we don't understand. We've named it dark energy. But naming isn't understanding. We've measured its effects, but not its nature. We've calculated its density, but not its origin. And the largest structures in the universe, the voids, might be the key to unlocking this mystery. Have you ever felt overwhelmed by how how much you don't know, by the vastness of your own ignorance. That's where cosmology is right now, regarding dark energy. We're like ancient humans who just discovered that the Earth orbits the Sun, realizing that our previous understanding was incomplete, that reality is stranger and larger than we imagined. But there's beauty in this not knowing. It means there are still profound discoveries waiting to be made. It means the universe can still surprise us. Let me share another fascinating connection between voids and dark energy. Some researchers have proposed that the acceleration of the universe isn't actually uniform everywhere, that it might be stronger in some regions than others. And where would these variations be most apparent? In the voids, where dark energy's effects are least masked by matter. A controversial study published in 2017 by a team led by Lawrence Dam suggested they'd found evidence for spatial variation in dark energy by analyzing void properties in different parts of the sky. Other researchers have challenged their analysis, arguing that the apparent variation could be explained by statistical fluctuations or observational biases. The debate continues. This is how science progresses, through careful measurement, bold hypotheses, rigorous challenges, and gradual refinement of understanding. The voids are at the frontier of this process. There's also a connection between dark energy and the ultimate fate of the universe. If dark energy remains constant at its current value, the universe will continue expanding forever, accelerating indefinitely. Galaxies beyond our local group will eventually recede beyond our cosmic horizon, disappearing from view as space expands faster than light can traverse it. In about 100 billion years, observers in the Milky Way will see nothing beyond our own galaxy. The rest of the universe will have raced away into invisibility. But if dark energy grows stronger over time, a scenario called phantom energy, the acceleration could increase without limit, eventually tearing apart galaxies, then solar systems, then planets, then atoms themselves, in what's called the Big Rip. Observations of void expansion can help us determine if this nightmare scenario is plausible. Conversely, if dark energy weakens or reverses, the expansion might eventually stop and reverse, leading to a big crunch where everything collapses back together. Again, voids provide crucial data to test this possibility. The voids are telling us about the future of everything. There's something profound about finding that the emptiest places in the universe are where the deepest mysteries hide. It's a pattern we've seen before in science. The most important things are often in the places we least expect. The key to heredity wasn't in complex organisms, but in simple peas in Gregor Mendel's garden. The key to relativity wasn't in dramatic celestial events, but in careful thought experiments about light and motion. The key to quantum mechanics wasn't in large-scale phenomena, but in the behavior of individual atoms and photons. And now, we're learning that the key to understanding the universe's fate, the nature of dark energy, the reason for acceleration, perhaps even the validity of general relativity itself, might be hiding in the cosmic voids, in the nothing, in the empty space we once dismissed as unimportant. The universe has a way of humbling us like this. Every time we think we understand what's important, we discover we were looking in the wrong place. Every time we think we've found the fundamental level, we discover there's something deeper still. as you breathe slowly in this moment, feeling your body settle into rest, consider this strange fact. The emptiness of space is not really empty. It's filled with dark energy, with something we can't see, but whose effects shape the entire cosmos. Every cubic centimeter of the void around us, of the space between stars, of the space between atoms, contains this mysterious energy. You are immersed in dark energy right now. It permeates your body. It fills the room around you. It extends outward through space to the edges of the observable universe, and it's pushing everything apart, slowly but relentlessly, writing the destiny of the cosmos. The voids amplify this effect, making it visible, measurable, undeniable. They're windows into the fundamental nature of space and energy and existence itself. And as our measurements become more precise, as our surveys map more of the universe, as our theories become more sophisticated, the voids will continue teaching us about the mysterious force that dominates everything. But dark energy isn't the only mystery hiding in the voids, because there's one particular void, or rather, one particular region that might be a supervoid that has cosmologists arguing about whether it's evidence for completely new physics, a connection to other universes, or perhaps the largest structure ever discovered. The story of the cold spot is where cosmic voids meet cosmic mysteries in ways that still decades after its discovery leave scientists searching for answers. What if there's a place in the universe that shouldn't exist? A region so anomalous, so statistically improbable, that some scientists have proposed it might be evidence of another universe colliding with ours, or a scar left over from the birth of reality itself. This place exists. It's called the cold spot. And, at its heart, might be one of the largest voids ever discovered, a supervoid so vast that it's leaving an imprint on the oldest light in the universe. If you're finding these cosmic mysteries as captivating as I do these questions that push the boundaries of what we think is possible, I'd be grateful if you'd like this video and subscribe to the channel. Your support allows us to keep exploring these edges of understanding together. Thank you. The story begins in 2004, though the data that revealed the mystery was actually collected years earlier. NASA's Wilkinson Microwave Anisotropy Probe WMAP for short had been mapping the cosmic microwave background, or CMB. This is the afterglow of the Big Bang radiation that has been traveling through space for 13.8 billion years, carrying information about the universe when it was only 380,000 years old. The CMB is remarkably uniform. Its temperature is almost exactly 2.725 Kelvin. Everywhere you look, that's about minus 270 degrees Celsius, just slightly above absolute zero. But there are tiny fluctuations regions that are slightly warmer or cooler by about 1 part in 100,000. These fluctuations are incredibly important. They're the seeds of all cosmic structure, the tiny quantum ripples from the inflationary period that grew over billions of years into galaxies and clusters and the cosmic web we see today. By mapping these temperature variations in exquisite detail, cosmologists can test their theories about the early universe, the nature of dark matter, and the properties of dark energy. When the WMAP team released their full sky map in 2004, something strange immediately caught astronomers' attention. In the southern celestial hemisphere, in the direction of the constellation Eridanus. There was a region about 5 degrees across, roughly 10 times the width of the full moon, that was unusually cold. How cold? About 70 microkelvins colder than the surrounding average. That might not sound like much 70 millionths of a degree, but in the extraordinarily uniform CMB, it stood out like a sore thumb. The WMAP team ran the statistics. What's the probability that such a large cold region would appear by random chance in the CMB? The answer was sobering, about 1 in 50,000. Not impossible, but highly unlikely. This became known as the CMB cold spot. And for the past 2 decades, astronomers have been arguing about what it means. Let me give you some context about why this matters. The CMB fluctuations we observe should follow very specific statistical properties based on our understanding of the early universe. There should be variations on all scales: small patches, medium patches, large patches, but the distribution of sizes and temperatures should match precise predictions from inflation theory. The cold spot doesn't quite fit these predictions. It's too large and too cold to be easily explained as a random fluctuation. Something unusual must be going on. The first question scientists asked was, is it even real? Could it be a measurement artifact? A glitch in the satellite's instruments? Contamination from foreground sources like dust or our own galaxy? The answer came in 2013 when the European Space Agency's Planck satellite, with even more sensitive instruments than WMAP, re-observed the same region of sky. The cold spot was still there. It was real. Whatever was causing it wasn't a mistake or an instrument error. It was something genuinely unusual about that region of the universe. So, what could explain it? The most conservative explanation is that it's simply a statistical fluke. Yes, the odds are 1 in 50,000, but we're observing the entire sky. With enough places to look unlikely, things do happen. It's like flipping a coin 16 times and getting heads every time unlikely for any specific sequence of flips. But if you flip coins billions of times, improbable sequences will eventually appear. Many cosmologists lean toward this explanation. After all, the universe is vast, and our sample size 1, observable universe, is quite limited. Stranger things might exist elsewhere that we simply haven't observed yet. But other researchers aren't satisfied with this answer. They've proposed more exotic explanations. In 2007, Laura Mersini-Houghton, a theoretical physicist at the University of North Carolina, made a bold suggestion the cold spot might be evidence of another universe. In her model based on string theory and eternal inflation, our universe is just one bubble in a vast multiverse. During the inflationary period, our bubble might have collided with another bubble, another universe, and the cold spot is the scar left by that collision. This idea captured public imagination, a collision with another universe. Evidence that we're not alone in the multiverse. Science fiction made real. But most cosmologists were skeptical. The collision model made specific predictions that didn't quite match observations, and there were simpler explanations that didn't require invoking the multiverse. One of those simpler explanations involves, you guessed it, a supervoid. In 2015, a team led by Istvan Sapudi at the University of Hawaii announced they had found an enormous void in the direction of the cold spot. Using observations from several telescopes, they mapped the 3-dimensional distribution of galaxies in that region. And and discovered an underdense area about 1.8 billion light-years across. This was exciting because supervoids can create cold spots in the CMB through something called the integrated Sachs-Wolf effect, or ISW for short. Here's how it works. As CMB photons, the light from the Big Bang, travel through space, they pass through regions of varying gravitational potential. When a photon falls into a gravitational well, like a galaxy cluster, it gains energy and becomes slightly bluer. When it climbs out of that well, it loses the same amount of energy and returns to its original color. Normally, these effects cancel out perfectly. The energy gained going in equals the energy lost coming out. But if the universe is expanding in an accelerating way, which it is due to dark energy, the gravitational potential changes as the photon passes through. The well becomes slightly shallower as space expands, so the photon loses a bit less energy climbing out than it gained falling in. The net result is that the photon ends up slightly more energetic, slightly bluer than it would have been otherwise. This is the ISW effect. Clusters make the CMB slightly warmer through this mechanism. Voids, which are gravitational hills rather than wells, make the CMB slightly colder. A regular void creates a small cold spot, but a supervoid, an extraordinarily large and empty region, could potentially create a larger cold spot. This is what Saputi's team proposed. The Eridanus supervoid, as they called it, might be imprinting itself onto the CMB. As photons pass through this vast underdense region, they lose energy through the ISW effect, arriving at our telescopes slightly colder than they would be otherwise. The discovery made headlines around the world. Largest structure ever found could solve cosmic cold spot mystery, the articles proclaimed. Finally, an explanation that didn't require parallel universes or breakdowns in fundamental physics. But there was a problem. When theorists calculated exactly how much cooling the Eridanus supervoid should produce through the ISW effect, they got a number that was smaller than the observed cold spot. The supervoid could explain maybe half of the temperature deficit, perhaps a bit more. But not all of it. This is where things stand today. The cold spot remains mysterious. Some researchers argue that the supervoid plus a statistical fluctuation together explain the observation. Yes, the supervoid alone isn't enough, but combined with a random cold patch, it could account for what we see. This seems like having your cake and eating it too, invoking both a special structure and chance. But it's not unreasonable. Multiple factors often contribute to observations in complex systems. Others point out that our understanding of the ISW effect in voids might be incomplete. Perhaps supervoids affect the CMB in ways we haven't fully modeled. Perhaps there are additional physical processes at work that we're missing. And a few holdouts still favor more exotic explanations. Some propose that the cold spot is a topological defect, a kind of cosmic scar from a phase transition in the very early universe, similar to cracks that form when water freezes. Others continue to explore multiverse collision scenarios, though these have fallen out of favor as models become more refined. The debate continues, and that's actually one of the beautiful aspects of science. It's comfortable with not knowing. It's okay to say, we don't understand this yet, and keep investigating. Let me tell you about some of the ongoing research. Astronomers are using increasingly powerful telescopes to map the Eridanus supervoid in greater detail. How empty is it really? What's its exact shape? Are there substructures within its smaller voids or filaments? The more precisely we characterize the void, the better we can calculate its expected ISW signature. Other researchers are searching for additional cold spots elsewhere in the CMB. Are there other regions with similar statistical properties? If we find several such anomalies, and they all correspond to supervoids, that would strengthen the ISW explanation. If we find cold spots without corresponding voids, that would suggest something else is going on. There's also work being done to improve our theoretical models of how voids evolve and how they interact with light passing through them. The ISW effect is well understood in principle, but calculating it precisely for a structure as large and complex as a supervoid requires sophisticated computer simulations. A study published in 2017 by Andras Kovac and collaborators used a different approach. Instead of looking just at the cold spot, they analyzed the ISW effect from all the supervoids they could identify in galaxy surveys, then stacked the signals statistically. They found that supervoids do produce measurable cooling in the CMB, but the effect is smaller than some earlier estimates suggested. This weakens, but doesn't eliminate the supervoid explanation for the cold spot. Here's what strikes me as particularly fascinating about this mystery. It demonstrates how interconnected different areas of cosmology are. To understand the cold spot, we need to understand the early universe, which created the CMB, the evolution of structure, which created the supervoid dark energy, which enables the ISW effect and statistical physics to calculate probabilities. It's a problem that sits at the intersection of multiple fields, and it reminds us that the universe still holds surprises. Despite our sophisticated theories and powerful instruments, we can still find things that don't quite fit, that challenge our understanding, that invite us to think more deeply. Have you ever encountered a fact that didn't fit your mental model of how the world works? That cognitive discomfort, that feeling of wait that shouldn't be possible, is actually a gift. It's telling you that your model needs refinement, that there's something to learn. The cold spot is giving cosmologists that gift right now. There's also something poetic about the idea that the emptiest place we've found the Eridanus supervoid might be leaving its fingerprint on the oldest light in the universe. That absence could mark presence in this way, that a void could cast a shadow, in a sense, though not a shadow of light, but a shadow of temperature. Let me address a common misconception about the cold spot. Sometimes people imagine it as a region of the actual sky that's colder, like a freezing patch of space you could fly through with a spaceship. This isn't correct. The cold spot is in the cosmic microwave background, which is everywhere around us. The CMB photons from that direction happen to be slightly less energetic than average, but you can't visit the cold spot any more than you can visit a particular moment in time. It's in the past, encoded in ancient light. What you could visit in principle is the Eridanus supervoid, the empty region of space that might be causing the cold spot. If you could somehow travel 1.5 billion light years in the direction of the constellation Eridanus, you'd find yourself in one of the least dense regions of the observable universe. Few galaxies, lots of empty space. And if you could see the CMB from there, if you could look back at the afterglow of the Big Bang, you'd see a cold spot in the opposite direction because you'd be inside the void looking out. The cold spot controversy has also sparked discussions about the philosophy of science. How much evidence do we need before we accept an extraordinary explanation like a multiverse collision? At what point does a statistical improbability become significant enough to demand a new physical mechanism? These are questions without clear answers. Science is partly about following evidence, but it's also about judgment, about weighing competing explanations, about balancing simplicity against explanatory power, about knowing when to trust your theories and when to question them. The cold spot teaches us humility. It reminds us that we're still in the early stages of understanding the universe. We've learned an enormous amount: the Big Bang, the expansion of space, the cosmic web, dark matter, dark energy. But there are still mysteries that we've barely begun to unravel. And many of those mysteries seem to be connected to the voids. These regions we once thought were simple, empty, boring. They turn out to be some of the most interesting and informative parts of the cosmos. As your breathing deepens and your thoughts slow, consider this strange fact. Somewhere in the southern sky, in the direction of Eridanus, there's a patch of ancient light that's slightly cooler than it should be. It's been cooling for over 13 billion years, carrying a message we're only now beginning to read. And that message might be telling us about the largest empty region in the known universe, or about the moment of cosmic inflation, or perhaps about the existence of other universes beyond our own. The cold spot is a window into the unknown, and like all good mysteries, the more we learn about it, the more questions it raises. But that's how discovery works. Each answer opens new doors. Each solution reveals deeper puzzles. The cold spot and its associated supervoid represent the cutting edge of cosmology, the place where observation meets theory, where data challenges models, where we're forced to think carefully about what we know and what we're still guessing at. But if understanding the cold spot is about looking backward, examining the traces of the ancient past, there's another aspect of cosmic voids that's about looking forward. Because the voids aren't static, they're growing, expanding, taking over more and more of the universe's volume. And if we follow this trend into the distant future, we arrive at a vision of the cosmos that's both beautiful and haunting. A universe where emptiness becomes the dominant reality, where the lights slowly go out, where the cosmic web unravels into isolated islands separated by ever-widening oceans of void. Imagine being an astronomer 100 billion years from now. You look up at the night sky with the most powerful telescopes available, searching for other galaxies, other worlds, other cosmic structures beyond your own, and you find nothing, just darkness, an empty universe stretching in all directions with no evidence that anything exists beyond your local cluster of stars. You would have no way of knowing that the universe was once rich with billions of galaxies. No way of discovering the Big Bang. No way of understanding cosmology. The evidence would have disappeared, carried away into the void. This is where the universe is heading. And understanding this future, this slow march toward emptiness, changes how we think about our place in cosmic time. If these contemplations about deep time and cosmic destiny resonate with you, I'd be honored if you'd like this video and subscribe to the channel. We're walking together through some of the most profound questions we can ask. Thank you for joining this journey. The voids are growing. Right now, at this moment, they're expanding. And they're expanding faster than the overall expansion of the universe. Let me explain what that means. The universe as a whole is expanding. Space itself is stretching, carrying galaxies away from each other. But this expansion isn't uniform. In dense regions like galaxy clusters, gravity is strong enough to overcome the expansion locally. Our local group of galaxies, for instance, isn't expanding. The Milky Way and Andromeda are actually moving toward each other, bound together by gravity, even as the space around us expands. But in the voids, where there's very little matter and gravity is weak, nothing holds back the expansion. Dark energy dominates completely. The voids expand at the maximum rate, and as they do, they push matter away from their centers toward their edges. This creates a feedback effect. As voids expand, they become less dense, which weakens their gravity further, which allows them to expand even faster. It's a runaway process. The voids are winning the cosmic tug-of-war between gravity and expansion. Computer simulations show this clearly. A team at the Max Planck Institute for Astrophysics ran a simulation in 2011 that tracked the evolution of cosmic structure over hundreds of billions of years. What they found was striking. The voids grow steadily, consuming more and more of the universe's volume. The filaments become thinner, the walls become more fragile, and the matter in the universe gradually concentrates into a smaller and smaller fraction of space. Think of it like a sponge drying out. At first, water fills many of the chambers, but as it dries, the water retreats, concentrating in fewer and fewer pockets, while most of the sponge becomes empty. That's what's happening to the cosmic web. The wet parts, the regions with galaxies, are shrinking. The dry parts, the voids, are growing. Now, let's follow this process into the deep future. Let's see where it leads. 10 billion years from now, about the time our sun will be nearing the end of its life, the universe will look broadly similar to today. There will still be billions of galaxies visible in the sky. The cosmic web will still be recognizable. But the voids will be noticeably larger. More of the universe's volume will be empty. 20 billion years from now, the changes become more dramatic. Many smaller galaxies will have merged with larger ones. The local group, for instance, will have fully coalesced the Milky Way, and Andromeda will have completed their collision, forming a giant elliptical galaxy that astronomers have nicknamed Milkomeda. The cosmic web will be coarser with thicker filaments and larger voids. 50 billion years from now, something significant happens. Galaxies beyond our local supercluster begin to disappear from view. Not because they're destroyed, but because the expansion of space carries them beyond what's called the cosmic event horizon. Their light can no longer reach us because space between us and them is expanding faster than light can traverse it. This is a consequence of dark energy. As the universe expands and becomes less dense, dark energy, which doesn't dilute with expansion, becomes increasingly dominant. The expansion accelerates. And as it accelerates, the portion of the universe we can observe shrinks. Think about that carefully. Our observable universe is currently about 93 billion light-years across. But this isn't a fixed boundary. It's defined by how far light can have traveled since the Big Bang. In an accelerating universe, this boundary doesn't keep expanding forever. Eventually, it begins to shrink. Galaxies that were once visible cross beyond the horizon and disappear from view. 100 billion years from now, a span of time roughly 7 times the current age of the universe, the observable universe will contain only our local group of galaxies merged into a single massive system. Everything else will have receded beyond the horizon. An astronomer in that era, looking out at the night sky, would see only their local galaxy surrounded by emptiness. They would have no evidence that other galaxies exist. No evidence of the cosmic web. No evidence even that the universe is expanding, because they'd have nothing to measure expansion against. Lawrence Krauss and Robert Scherer explored this scenario in a remarkable paper published in 2007. They called it The End of Cosmology. Their point was profound. We happen to live in a special epoch, what they call the golden age of cosmology, when the evidence for the Big Bang for cosmic expansion, for the existence of billions of galaxies, is still available to observe. But this age won't last forever. Future civilizations, if they exist 100 billion years from now, will be cosmologically blind. They'll be living in what appears to be a static, finite universe consisting of a single galaxy surrounded by eternal darkness. They might develop physics, chemistry, biology, but they'd have no way of discovering cosmology as we understand it. The evidence will have vanished, carried away by the expansion of space. This raises a haunting question. What evidence has already disappeared from our view? What could we have learned about the universe if we'd existed earlier, when more of it was visible? Are there truths about reality that are now forever beyond our ability to discover? Because the proof has expanded beyond our cosmic horizon, we can't know. By definition, we can't observe what we can't observe. But the future evolution of voids teaches us that cosmic evidence is time-limited. The universe doesn't preserve all its secrets forever. Let's continue further into the future. 1 trillion years from now, a time span that dwarfs current cosmic age by a factor of 70 star formation, will have largely ceased. Most of the gas that forms new stars will have been used up or locked away in stellar remnants, white dwarfs, neutron stars, black holes. The universe will be darker than it is today, lit only by old, dying stars. The voids will be enormous by this point, spanning billions of light years. They'll dominate the volume of space. The remaining matter will be concentrated in isolated island galaxies, separated by vast, empty gulfs. 100 trillion years from now, even the longest-lived stars will have burned out. The universe will enter what cosmologists call the degenerate era, populated by stellar remnants, cold white dwarfs, neutron stars, and black holes slowly orbiting each other in the darkness. The voids will contain essentially nothing. No light, no heat, just the faint radiation of dark matter particles occasionally interacting. And this is where things get truly strange, because even black holes don't last forever. Stephen Hawking showed in 1974 that black holes slowly evaporate through a quantum process now called Hawking radiation. The rate is extraordinarily slow. A black hole with the mass of the sun would take 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. A number so large, it's essentially meaningless to human intuition. But given enough time, all black holes will evaporate, and when they do, they'll leave behind only photons and elementary particles, which will quickly disperse into the expanding void. 10 to the power of 100 years from now, a googol years far beyond the lifetime of any black hole, the universe will be almost perfectly empty. Just scattered particles spread so thinly that they almost never encounter each other in a space that continues to expand forever. This is called the Big Freeze, or heat death, the ultimate fate of a dark energy-dominated universe. The voids will have won completely. The universe will be void. There's something both terrifying and beautiful about this vision. Terrifying because it represents the ultimate dissolution of everything, all complexity, all structure, all possibility, reduced to sparse particles in infinite emptiness, but beautiful because it represents a kind of return to simplicity. The universe began in a state of near-perfect uniformity and will end in a state of near-perfect emptiness. From order to chaos to a different kind of order. But here's a crucial point that I want to emphasize: this future is not certain. It depends on dark energy behaving the way we currently think it does, remaining constant in density, even as space expands. If dark energy changes over time, the future could be very different. If dark energy weakens, the expansion might eventually stop and reverse, leading to a big crunch where everything collapses back together. The voids would shrink instead of growing. Matter would concentrate rather than disperse. Eventually, all of space would compress into a singularity, possibly leading to another Big Bang and a cyclic universe. If dark energy strengthens a scenario called phantom energy, the expansion could accelerate without bound. In this case, the voids wouldn't just grow, they'd eventually tear apart everything. First, galaxy clusters would unbind. Then galaxies themselves would be ripped apart. Then solar systems. Then planets. Then molecules, then atoms. Finally, even atomic nuclei would be torn asunder in what's called the Big Rip. Fortunately, current observations suggest that dark energy is most consistent with being a cosmological constant, unchanging with time. This points toward the Big Freeze scenario, rather than the Big Crunch or Big Rip. But our measurements aren't perfect. There's still room for surprise. And here's where the voids become crucial again. By measuring how voids expand at different cosmic epochs, different times in the universe's history, we can determine whether dark energy is truly constant or changing. The voids are our laboratories for testing these scenarios. This is why research on voids isn't just about understanding the present. It's about predicting the future, about knowing the ultimate fate of everything. Have you ever contemplated your own mortality? Truly sat with the fact that you won't exist forever? There's something both sobering and liberating about that awareness. It makes the present moment more precious. It encourages us to appreciate what we have while we have it. The cosmic voids teach us a similar lesson on a universal scale. The universe we observe, rich with galaxies, structured in its magnificent web, is temporary. It's a phase, a moment in cosmic time, not the permanent state of reality. This awareness changes how we think about our place in the cosmos. We're not just small in space, we're small in time. We exist during a brief window when the universe is complex enough to support life and observers, but still transparent enough that we can study its structure and history. We're living in the golden age of cosmology when the evidence is still visible. There's also something profound about realizing that emptiness is the universe's destination. We started our journey learning that voids make up 80% of the universe's current volume. But that's just the beginning. The universe is evolving toward being almost entirely void. Emptiness isn't an aberration, it's the norm. It's where everything is heading. This connects to themes we've explored throughout this journey. Emptiness as active rather than passive, absence as powerful rather than weak. The void, not as nothing, but as the ground state of reality, what remains when everything else is stripped away. In some Eastern philosophies, emptiness or void is considered the fundamental nature of existence. All forms arise from emptiness and return to emptiness. What we perceive as solid and permanent is actually temporary and illusory. Only the void is eternal. Modern cosmology is arriving at a similar conclusion through very different means. The universe begins in near uniformity, develops temporary structures through gravitational collapse, and ultimately returns to near emptiness through accelerating expansion. The structures we see, the galaxies, the stars, the planet's life itself, are all temporary fluctuations in an ocean of void. But, and this is important, that doesn't make them meaningless. Temporary doesn't mean worthless. The fact that a sunset lasts only minutes doesn't diminish its beauty. The fact that a song ends doesn't make it less moving. The fact that life is finite doesn't make it less precious. The same applies cosmically. The fact that the cosmic web will eventually dissolve doesn't make it less magnificent. The fact that galaxies will disappear beyond horizons doesn't make studying them less worthwhile. If anything, the temporary nature of cosmic structure makes it more remarkable. We exist during the era when the universe is interesting, when things happen, when complexity is possible, and we're conscious, able to observe, to understand, to appreciate. That's extraordinary. As your breathing slows and your muscles relax, settling into the quiet of this moment, perhaps you can feel a resonance between your own experience and these cosmic timescales. You too are a temporary structure atoms organized briefly into a pattern called you before returning to the universe. Like a galaxy, like the cosmic web, like all forms, you're a momentary eddy in the flow of existence. But that moment matters. Your consciousness, your experiences, your capacity to wonder about these vast questions, these are real, even if temporary. They're part of what the universe does during its complex phase, during its time of structure and possibility. The voids show us that impermanence is built into the fabric of reality. But they also show us that impermanence doesn't prevent meaning. The cosmic web exists now, even though it won't exist forever. Galaxies shine now, even though they'll eventually go dark. Life happens now, even though it will eventually end. Now is what we have, and the voids growing slowly but inexorably, taking over more of the universe with each passing eon, remind us to pay attention to now, to the brief window of complexity and consciousness that we're privileged to inhabit. These thoughts about time and change and destiny bring us to the end of our journey through the cosmic voids. We've explored their discovery, their structure, their effects on galaxy evolution, our location within them, their connection to dark energy, and their role in shaping the future of everything. But what does all this mean? How do we hold all these pieces together? What wisdom can we draw from the largest structures in the universe? from the emptiness that defines everything. We've traveled far together through this exploration, from the shocking discovery of the Bode's void in 1978 to visions of a universe 100 trillion years from now, from the cosmic web's intricate architecture to the profound mysteries of dark energy, from our own cosmic address on the edge of the local void to the enigmatic cold spot that still puzzles scientists today. And through it all, one theme has emerged. Again and again, emptiness is not absence. The voids are not nothing. They're active participants in the grand drama of cosmic evolution, shaping, pushing, revealing, teaching. Let me gather these threads together, because there's something profound here that extends beyond astronomy, beyond physics, into how we understand existence itself. The cosmic voids teach us first and foremost about structure emerging from simplicity. The universe began in a state of extraordinary uniformity, tiny quantum fluctuations in an otherwise smooth distribution of matter. No plan, no blueprint, no designer arranging where galaxies would go, just gravity expansion and time. And from these simple ingredients, the cosmic web emerged. Filaments formed, walls developed, nodes appeared where filaments intersected, and the voids, those vast empty chambers, arose naturally as matter flowed away from underdense regions toward overdense ones. The voids weren't created separately from the web. They are the web. You cannot have filaments without the spaces between them. You cannot have structure without emptiness to define it. The cosmic web and the cosmic voids are two aspects of the same phenomenon, the large-scale architecture of reality. This principle appears throughout nature. In music, silence defines rhythm and melody. In language, the spaces between words make speech comprehensible. In architecture, the empty rooms give purpose to the walls. In consciousness itself, the gaps between thoughts allow awareness to exist. We tend to focus on the things, the notes, the words, the walls, the thoughts. But the spaces between are equally essential, perhaps more essential. Because without emptiness, without intervals, without voids, everything would be noise, chaos, meaninglessness. The universe understands this at the deepest level. 80% void, 20% matter. The ratio isn't accidental. It's what allows structure to form, to persist, to evolve into complexity. Second, the voids teach us about perspective and observation. We discovered that we live on the edge of the local void, not in some typical average location, but in a specific place with specific properties. And this location shapes everything we observe. Our measurements of cosmic expansion are influenced by the void pushing us from behind. Our view of the universe is colored by where we happen to be standing. The evidence available to us is determined by when we exist in cosmic time. This is a humbling realization. It reminds us that all observation is local. All knowledge is contextual. We're not seeing the universe from some privileged objective viewpoint. We're seeing it from here, from now, through instruments and minds shaped by our particular circumstances. And yet, despite these limitations, we can still learn. We can still discover. We can account for our location, correct for our biases, and approach truth asymptotically, even if we can never quite reach it absolutely. The history of astronomy is a history of decentering, of realizing we're not as special as we thought. Earth isn't the center of the universe. The sun is an ordinary star. The Milky Way is one galaxy among billions. And now we learn that even our location in the cosmic web is somewhat atypical. Each decentering feels like a loss, but it's actually a gain in understanding, in perspective, in truth. We see more clearly when we recognize our own particularity. Third, the voids teach us about impermanence and change. They're growing, expanding, taking over more of the universe's volume with each passing billion years. The cosmic web we observe today is temporary, a phase in the universe's evolution from near uniformity to near emptiness. This long view of time changes how we think about the present. We're living during the universe's complex era, when structures exist, when light shines, when observers can observe. But this era won't last forever. Eventually, the voids will win. Emptiness will dominate completely. Does this make the present less meaningful? I don't think so. If anything, it makes it more precious. We exist during the brief window when the universe is doing something interesting, when matter organizes itself into galaxies and stars and planets and life, when consciousness arises to contemplate it all. The Buddhist concept of anicca impermanence holds that nothing lasts forever and that suffering arises from our attachment to permanence. By accepting impermanence, we can appreciate what exists without clinging to it. The voids embody this principle cosmically. Everything is temporary. The galaxies will fade. The structures will dissolve. Even the atoms will eventually decay. But right now, in this moment, they exist. And that existence is complete in itself, requiring no justification beyond the fact that it is. Fourth, the voids teach us about the unknown. Dark energy makes up 68% of the universe's energy content, and we don't know what it is. The voids where dark energy's effects are most apparent are laboratories for studying this mystery. But despite decades of research, despite increasingly sophisticated observations, we're still uncertain about dark energy's fundamental nature. This is okay. Science isn't about having all the answers. It's about asking better questions, about refining our uncertainties, about being comfortable saying, "We don't know yet," while continuing to investigate. The cold spot mystery captures this perfectly. Is it a statistical fluke, a supervoid's imprint, a scar from cosmic inflation, evidence of the multiverse? We don't know. Multiple teams of brilliant scientists have studied it for 20 years, and we still don't have a definitive answer. But we've learned a lot in the process. We've improved our understanding of the ISW effect. We've mapped cosmic voids in greater detail. We've refined our statistical methods. We've developed better theories of structure formation. The mystery has driven progress even without being solved. This is how science works. Not through sudden revelations that answer everything, but through gradual accumulation of understanding. Through patient observation, through careful reasoning, through following the evidence wherever it leads, even when it leads to more questions. Fifth, and perhaps most profoundly, the voids teach us about the nature of influence and power. We usually think power comes from presence, from action, from force applied. But the voids show us that absence can be equally powerful. The voids push galaxies away through their expansion. They shape galaxy evolution by providing isolation. They reveal dark energy by removing the complications of dense matter. They define the cosmic web by being the spaces between the filaments. Their emptiness is their power. This inverts our usual assumptions. We spend so much energy on doing accumulating, filling, accomplishing. We fear emptiness, empty schedules, empty space, empty minds. We rush to fill every void. But what if emptiness is where growth happens? What if the spaces between activities are when integration occurs? What if mental quiet is where creativity emerges? What if absence creates possibility? The cosmic voids suggest this is true. They're not sterile wastelands, they're dynamic regions where different physical processes dominate, where galaxies evolve differently, where space expands most freely. The void galaxies we discussed, smaller, bluer, more actively forming stars, thrive in their isolation. The emptiness doesn't limit them, it liberates them. There's a parallel here to sleep, to the theme that connects all the stories we share on this channel. Sleep is a kind of personal void, a time when we withdraw from activity, from stimulus, from conscious thought. We spend a third of our lives in this state of apparent nothingness. But sleep isn't nothing. It's when memory consolidation happens, when cellular repair occurs, when the brain processes and integrates the day's experiences, when creativity incubates. The emptiness of sleep is where restoration happens. Just as the cosmic voids are essential to the structure of the universe, sleep is essential to the structure of a healthy life. Both are forms of emptiness that enable complexity. Both are absences that shape presence. And as you rest here now, breathing slowly, feeling your body settle into stillness, perhaps you can sense this connection. You are participating in the same principle that structures the cosmos. You are embracing emptiness as a generative force. You are allowing the void to do its work. The physicist John Wheeler once said that matter tells space how to curve, and space tells matter how to move. But we might extend this voids, tell matter where to flow, and matter tells voids where to grow. They're partners in a cosmic dance that's been unfolding for 13.8 billion years and will continue for trillions more. We've learned that the universe is mostly empty, but that emptiness is active, structured, meaningful. We've learned that we live on the edge of a void, and that this location shapes our observations and our history. We've learned that the future belongs to the voids, that emptiness is the universe's destination. And we've learned that mystery remains, that the cold spot dark energy and the ultimate nature of the voids continue to challenge our understanding. But perhaps the deepest lesson is this: the universe didn't have to be interesting. It could have remained uniform. It could have collapsed immediately after the Big Bang. It could have expanded so rapidly that no structures formed. But instead, through a combination of physical laws, initial conditions, and quantum fluctuations, it created structures. It organized itself into patterns. It made places where galaxies form, where stars ignite, where planets condense, where life emerges, where consciousness arises to ask questions about its own existence. The voids are part of this story, not obstacles to be overcome, but essential characters in the narrative. The silence that makes the music meaningful, the darkness that makes the light visible, the emptiness that gives shape to everything. And we, you and I here and now, are part of this story too. We're patterns formed briefly in the universe's complex era. Configurations of atoms that can contemplate the voids, map their boundaries, measure their expansion, wonder about their meaning. We're the universe observing itself, thinking about itself, trying to understand itself. That's not a small thing. That's not insignificant, even if it's temporary, especially because it's temporary. It matters. The voids remind us to appreciate the structures while they last, to observe carefully while we can, to seek understanding during our brief window of cosmic clarity, to embrace both the fullness and the emptiness, recognizing that neither can exist without the other. As this journey comes to rest, as your thoughts drift towards sleep, carry this awareness with you. You are connected to the largest structures in existence. The same principles that shape cosmic voids shape your need for rest. The same impermanence that governs galaxies governs every moment of your life. The same mystery that pervades the universe pervades your consciousness. You are cosmically ordinary, made of common atoms, governed by universal laws, subject to the same forces that shape everything. And you are cosmically extraordinary, a configuration that can know it exists, that can wonder, that can seek understanding. The voids don't diminish this. They enhance it, because they show us that the universe is stranger, more structured, more wonderful than we imagined. That emptiness is creative, that silence is eloquent, that nothing is something. Sleep well, friends. Rest in the knowledge that you're part of something vast and ancient and ongoing. That the atoms in your body were once floating in cosmic voids. That the breath you take is shaped by the same expansion that creates supervoids billions of light years across. That the stillness you seek mirrors the stillness at the heart of the cosmos. The voids are all around us, within us, before us, after us, not as threat or absence, but as foundation and possibility, as the space where everything can emerge and to which everything returns. Thank you for walking this path with me through the cosmic voids, for sitting with these big questions, for bringing your attention and presence to this exploration of the universe's empty spaces. The cosmos has many more stories to tell, mysteries waiting in the darkness between stars, wonders hiding in the quiet corners of existence. And I hope you'll join me again as we continue exploring them together, one peaceful journey at a time. Until then, may you find your own balance between structure and void, between doing and being, between the fullness of experience and the emptiness that makes it possible. Rest well in the stillness that shapes everything.